Thank you very much. I would like to thank the organizers for this kind of opportunity to speak in this very interesting talk, very interesting workshop. And what I will talk about is some related to Talenti comparison result. I will say in few minutes what I mean by Talenti comparison result for solutions to PDs. I start by saying that for me now and in the sequel, omega will be an open bounded set, and in order to in the sequel maybe that its boundary needs to be Lipschitz, and start by defining what I mean by this mu, u star, and u sharp. So u is a measurable function, and I will denote by mu of t the Lebesgue measure of its super level set. This is a decreasing function, and once you have defined the distribution, mu is called the distribution function of the function u, and once you have defined the function mu, you can define its generalized inverse u star of s, defined that as the supremum of all t such that mu of t is greater than s. This is a function which is called the decreasing rearrangement of u, which is a one-dimensional function decreasing in the set 0. Then you can define the Schwarz symmetrized of u, which is the function u star computed here, where omega n is the measure of the unit ball in Rn, and this is the modulus of x to the power n. And this is a function which is defined in what I will call omega sharp, the ball with the same measure as omega. This is a function which is radially symmetric. All its level set are balls, and is decreasing along the radii. The main property is that u star, and u sharp share the distribution function. Then, since they share their distribution function, they have the same LP norm whenever one of them belongs to LP. So the norm of u in LP is the same than the norm of u in omega, is the same than the norm of LP sharp in omega sharp, which is the same of the norm of u star in LP of 0 measurable. So the procedure of symmetrizing a function, if you pass from u to u star or from u to u sharp, you preserve the LP. No. This is a picture that can show you, this is u star, the one-dimensional decreasing rearrangement, and all the super level set have the same measure, so they share the distribution function, while this is u sharp. You take a function, take the super level set, and each super level set becomes a ball centered in the origin, and it is the measure of the super level set, and you obtain a function which is radially symmetric, decreasing along the radii with the same measure of the super level, with the same distribution function of the initial function, and so they have the same LP nodes. I wrote here some other properties that this is the Hardy-Littlewood inequality, which states that if you have the product of two functions, then this is maximized if you substitute u with u sharp and v with v sharp, the Schwarz rearrangement. In particular, when one of the two is the characteristic function of a super level set, you have that the integral of the function f on the super level set is less or equal than the integral between 0 and mu of t of the star. What I mean by comparison result, and comparison results are results which essentially take the solution of a problem with of a PDE with Dirichlet boundary condition, Robin boundary condition, or Neumann boundary condition, and try to compare this solution in a general set omega with the solution in a symmetrized set. And we will see that the Dirichlet the boundary conditions play a crucial role in the sense that the behavior of the comparison result may change when you pass from Dirichlet to Robin to Neumann. I want to recall the one other property of the symmetrization of the procedure of a symmetrized function, which is the Pauli-Azzigo principle. The Pauli-Azzigo principle asserts that whenever you have a function u which belongs in W1P0 for some p greater or equal than 1, then its Schwarz rearrangement belongs to 1P0 of omega sharp. And when you pass from the LP norm of the gradient to the LP norm of the gradient of U sharp, this LP norm decreases because you have a symmetric function and it is much more elegant the way to way from 0 and then away again to 0. And so the Schwarz symmetrization preserves the LP norm of the function, but decreases the energy. The Pauli-Azzigo principle has a lot of consequences. One of these consequences is the Faber-Krahn inequality, which asserts that if you take the first Dirichlet Laplacian eigenvalue, that is the first Laplacian eigenvalue with Dirichlet boundary condition, then this inequality holds true. This inequality asserts that the first Laplacian eigenvalue, if you want to minimize it in the class of sets with given volume, the minimum is on the ball. And the inequality is sharp in the sense that whenever equality occurs, then omega is equivalent to a ball. This is a consequence of the Pauli-Azzigo principle because the first Dirichlet Laplacian eigenvalue has a variational characterization because it is the minimum on H10 of omega of the quotient between the L2 norm of the gradient divided by the L2 norm of the function W. And so this minimum is achieved on the function u, which is the first eigenfunction of the Laplacian. And so if lambda 1 equals this Rayleigh quotient computed on the first eigenfunction, if you pass from u to its Schwarz symmetrized, the Rayleigh quotient decreases because the numerator decreases by Pauli-Azzigo principle, while the denominator remains the same since Schwarz symmetrization preserves the L2 norm. Then this is not an eigenfunction, but is a good test function in the Rayleigh quotient in omega sharp. So this is greater or equal than the minimum of the very same Rayleigh quotient computed on omega sharp, which is nothing but the first eigenvalue in the ball with the same measure. So the Faber-Krahn inequality is a direct consequence of Pauli-Azzigo principle. The same application of Pauli-Azzigo principle can be done for proving the Sembenan conjecture, which states that among all bars with the cross-section of a given measure, the circular one has the largest torsional rigidity. And what I mean by torsional rigidity, the torsional rigidity is the L1 norm of the solution of these PDs minus Laplacian of u equal to 1 with the Dirichlet boundary condition. But even in this case, it's reciprocal by obvious integration by part and derivation. Okay? 1 over the torsion is a minimum of a Rayleigh quotient which is very similar to the one involved in the case of the eigenvalue, but here you do not have the integral of the test function squared, but the integral squared. but this is achieved, this Rayleigh quotient on the solution of this problem. So once again, if you apply Pauli-Azzigo principle, you have that 1 over t, which equals this quotient, decreases if you pass from u to u sharp, because the numerator decreases by Pauli-Azzigo principle, while the denominator remains the same because it's the L1 norm of a function. And so you have again a good test function in omega sharp, and so you discover that 1 over t is minimum on both, and then t is maximum. So the torsion rigidity achieve its maximum in the class of set with given volume on the board. Talenti result, how you can insert Talenti result in this kind of applications. Talenti result, which is a result obtained in 1976 by Giorgio Talenti, states essentially this fact. I write its result for the Poisson equation, but it can be proved for a general operator, nonlinear, with lower order term, with the gradient drift term. You can generalize the Talenti result. A lot of version, but this is its simplest statement. I will call by P of D the problem the problem minus Laplacian of u equal to f in omega, and here I consider the Dirichlet boundary condition. P sharp of D is the very same problem minus Laplacian of v equal to the right hand side is symmetrized. Instead of f, you have f sharp, which is the Schwarz symmetrized of the function f, and you have also symmetrized the domain. Then Talenti result states that in the class of Poisson equation, when you have fixed, where you have fixed the measure of the domain and rearrangement of the solution, then the radial solution is the largest possible. In the sense that you can compare the rearrangement of u sharp pointwise with the solution of the radial problem in the ball with the same measure as omega. And you can also compare the L2 norm of the solution for Q less or equal than 2. You understand immediately that the solution to the radial case can be written in terms of a norm of f. And so this estimate, which holds pointwise, gives a priori estimates for solution to such a problem in terms of norm of f, solution which a priori estimates which are sharp with the best constant, and also this results is as a rigidity version in the sense that whenever a quality occurs, everything is really symmetric. And so this is now a classical result that you can see how it implies both Saint-Venant inequality and Faber.
Sorry, on the previous slide, what is? Oh, is this 2 here? The
yes, this is 2.
Okay.
Yes. And so Talenti result from if you assume Talenti result proved, you can deduce Saint-Venant and Faber-Ecran.
Q is less than 2 but bigger than 1.
What? You? Yes. Thank you. Why you can obtain why Talenti implies Saint-Venant is immediate result, because if you consider the solution, the torsion function, which is the solution of this Poisson equation with the right hand side equal to 1, then whenever you symmetrize this problem, omega becomes omega sharp, but the right hand side does not change, remains 1. And so Talenti results states that the rearrangement of the torsion function is pointwise less or equal than the solution, the radial solution of the symmetrized. If you integrate both over omega sharp, you obtain that the integral of the left-hand side, which is exactly the torsion in omega, because the L1 norm does not change when you pass from U to U sharp, is less or equal than the L1 norm of the solution, the radial solution, which is the torsion in omega sharp. So Talenti is much stronger than Neumann. Talenti provides a point-wise comparison between the two solutions, and so you can compare all the LP norm, even the infinity, but you have the consequence that Neumann holds true. And also you can deduce the Faber-Cran inequality. Why? Because if you consider the eigenvalue problem for the Laplacian with the Dirichlet boundary condition, and you symmetrize this problem, in the sense that omega becomes omega sharp, and the right-hand side becomes lambda 1 times U sharp, so you have symmetrized the right-hand side, then if you multiply this equation formally by the solution zeta, and you integrate by part, you have that lambda 1 equals this quotient, which is the quotient over omega sharp of the gradient of zeta square divided by U sharp times zeta. But U sharp is smaller or equal, is pointwise less or equal than zeta, because this is the Talenti result, which asserts that the Schwarz symmetrization of U is less or equal than the solution in the radial case. And so if you pass from U sharp to zeta here, the quotient decreases, but this is greater or equal than lambda 1 sharp, because once again zeta is a good test function. And so Talenti implies Faber-Cran. But only a remark. Here, in order to decrease, it's enough, it would be enough to compare the L2 norm. So if you have, if Talenti results hold in a weaker version, in the sense that you are not able to compare the solution pointwise, but only in the L2, if you have only an L2 version of the comparison, you can, by using Schwarz inequality, Cauchy-Schwarz inequality, you can prove in the same way that the Faber-Cran follows directly by a comparison. What happens if you change the boundary condition? And if you pass from Dirichlet to Robin or to Neumann? Okay, to Robin, I can say that the first Robin eigenvalue, for me, beta is a positive parameter. And the first Robin eigenvalue is defined as the minimum of this quotient. In this quotient, you have the numerator, which involves an energy integral and a surface term, which depends on the parameter beta, divided by the L2 norm of W. Okay? The minimum is achieved on the solution of this problem, which is the first Robin eigenfunction for the Laplacian. And so it satisfies the equation minus Laplacian of U equal to this number times U, while on the boundary, the condition is a condition which is a linear, which involves a linear combination of the normal derivative plus beta times U. And so what happens? That the Faber-Cran inequality still holds true. It was proved by Bossel in dimension 2 and by Danners in higher dimension, but Pauli-Azzigo principle cannot be used, because the Pauli-Azzigo principle states that the energy integral decreases whenever you have a zero boundary condition. Here, in general, if you pass from W to W sharp, it is not true that the whole numerator decreases, because you have a surface integral that you can. And so the proof by Bossel and Danners does not make use of rearrangement and does not make use of Pauli-Azzigo principle because of it. does not work. And the very same situation occurs for the torsion in the case torsion function in the case of Robin boundary condition. Once again, you can define 1 over the torsion as the minimum of a Rayleigh quotient. This is the same numerator that you have in the case of the eigenvalue, and in the denominator you have the L1 norm squared. This minimum is achieved on the solution of this problem minus Laplacian of u equal to 1 in omega, but the condition are the Robin on the boundary. And the torsion is once again the L1 norm of this function. There is a result analogous to the Saint-Venant conjecture of, in the case of the Dirichlet boundary condition. Also true that the torsion rigidity in the case of Robin boundary condition is maximum also in the class of domains with given volume. And this has been proved by Bucure and Giacomini in 2015. Once again, they cannot use because at this time it seems that you cannot be able to use. What happens to Talenti result in the case of Robin boundary condition? In the sense that it is possible to obtain something similar to the case of the Dirichlet boundary condition. And so it is possible to have to employ the symmetrization techniques in order to have comparison result even in the Robin case. The answer is yes and no, in the sense that differently from the case of the Dirichlet boundary condition, the comparison result is sensible to dimension. In the sense that, and this is a result provided by myself and Geraldine Karlonich in the 2023, in the sense that if you consider a non-negative function and a positive parameter beta, you consider the Poisson equation in omega with Robin boundary condition on the boundary. Then you consider the symmetrized problem, which is the same Poisson equation in a ball with the same measure, and with the right-hand side, which is Schwarz symmetrization of this right-hand side, and the boundary condition remains the same, Robin. What happens? In the case of a general F and in dimension 2, you can have L1 comparison between the solution and L2 comparison between the solution. No comparison for L infinity norms holds true in general. So this means, by remarks that I made before, that since you have for general F the L2 comparison, you can prove the Faber-Ekran inequality by using rearrangement. In the very same way that I used in the case of the Dirichlet boundary condition, because I said that the L2 comparison it's enough in order to gain the Faber-Ekran inequality. In dimension greater or equal than 3, you can prove only comparison in Lorentz spaces, no comparison in LP spaces. We have a counterexample in both of these, for this. So you can see that differently from the Dirichlet boundary condition, these comparisons are sensible to the dimension. Dimension 2, L1 and F2, and greater or equal than 3, only a Lorentz space. When F is equal to 1, so in the case of the torsion rigidity, then in dimension, once again, the comparison is sensible to dimension. But in dimension 2, you can have a pointwise comparison, so you can recover the Talenti result completely. In dimension greater or equal than 3, you are able to compare only the L1 norm, and we do not know what happens to the L infinity.
Excuse me, what are Lorentz spaces?
No, I want okay, Lorentz spaces are defined by considering an integral which involves power of the measure of the distribution function times a suitable power. When here you are in the same group. Yes, one the weakest spaces is the ones where Q is infinity. It's one, and when P and Q are the same, you have this. Back to the counter example, if we consider this in this problem, the function f, which is one in the ball with radius 1 and 0 in a smallest ball, this is its rearrangement. And then if you, for a suitable value of the parameter, in dimension 2, the L infinity norm of the solution U is greater than the radial one. In dimension 3, the L2 norm of the solution in the non-radial case is greater than. So you do not have the L2 comparison in dimension greater than 3, and you do not have the L infinity comparison in dimension 2. This means that you cannot have comparison for anything.
What about beta, the difference in beta
Or what?
of this issue?
Oh,
I mean,
clearly for
beta's-
beta very large, you have to go to the Talenti result, because when beta goes to infinity, you are going over versus the Dirichlet dimension. So all this counter example works for beta small, yes. And so these are the Lorentz spaces. And as I said before, in the same way, one can prove the Faber-Cran inequality for the first Robin eigenvalue using the L2 comparison in dimension greater, in dimension equal to 2. This is the best result that we have obtained.
So the relation between the two exponents P and Q, since P equals Q is not allowed, but there
No.
is P less than Q or P greater than Q. What
In
is-
the
in the Lorentz case, yeah.
in the Lorentz case, it depends. The
Ah.
P and Q are related to the dimension.
Okay.
Yes. You have a bound on P, which is less or equal than a function on the dimension, and Q is the integral. You do not obtain the results in Lorentz spaces. But in the Neumann case, yes. Okay, what happens in the case of Neumann boundary condition? So now I will focus on Poisson equation, and I will change again the boundary condition, and I will go to the Neumann boundary condition. I only want to recall you what is a set which has the property that it holds true, a set for which holds true a relative isoperimetric inequality. I say that omega is a set, for which holds true a relative isoperimetric inequality if there exists a positive constant such that for any subset of omega, this measure, the measure of the perimeter inside omega, the relative perimeter of E with respect to omega, is greater or equal than the suitable power of the minimum between this measure and this measure. For this set, there exists a result proved in 1979 by Maderna and Salsa for the Robin, for the Neumann boundary condition. So assume that F is equal to with 0 mean, and let us consider the solution to the Poisson equation with the Neumann boundary condition. And omega is a set with a relative constant, a relative isoperimetric constant. What they are able to prove is a comparison result of the solution of the Neumann problem, solution which is the comparison is the following one. Consider a function W which is U solution minus a constant. The constant is chosen in such a way that the measure of u minus k greater or equal than 0 and u minus k less or equal than 0 equals half of the whole measure, then they are able to say that the positive part of this rearrangement is less or equal than a constant, which depends on the relative constant of the, which depends on the relative isoperimetric constant in omega, times the solution of this problem, which is a Dirichlet problem, in a ball which has the measure, which is half the measure of the total space. So they are able to compare the solution of a Neumann problem somehow in a sharp way, but with the solution of a problem which is symmetrized, but the set as the measure which is half the measure of the whole space, and the Dirichlet boundary and the boundary conditions are changed from Neumann to Dirichlet, because essentially they consider the positive part and the negative part of the solution of the Neumann problem, and they symmetrize it separately. And they compares the positive part of the solution of this with the solution of the Poisson equation with the Dirichlet boundary condition in a half ball, and the negative part with the negative part. And this was
What's the F plus and minus?
F plus is the positive part of F symmetrized and the negative part symmetrized. So V plus solves with the F plus and V minus with F minus. What we have done in order to try to compare Neumann with the Neumann. This is a result that in a second I will summarize, proved by myself, Carlo Nitsch, and Antonio Celentano, which is a PhD student in our university. So we consider the following Neumann problem: minus Laplacian of u equal f in omega, and normal derivative constant on the boundary, but the constant cannot be 0. Constant, but not 0. Assume f greater or equal than 1 and symmetrize this problem. How? The Laplacian remains the Laplacian. The right-hand side, instead of f, you have f sharp, which is its Schwarz rearrangement, and omega is omega sharp, the ball centered at the origin with the same measure. The normal, the constant changes in the sense that the normal derivative of u is c, the normal derivative of u is c sharp. What is the relation between the two? Obviously, integrating the equation, you have that minus c times the perimeter of omega equals the L1 norm of f. The very same equality for the radial case, and so minus c sharp times the perimeter of omega sharp equals the L1 norm of f sharp, but these two are the same, and so the relation between the two constants is that the quotient between the two constants equals the quotient between the two perimeters. Once you have this, you can prove the following result in the Talenti style, once again sensible to dimension. Okay, assume that you have a non-negative solution of the non-symmetric problem, and if you fix such a normalization, you have to do, because otherwise you have infinite solution. If you fix such a normalization that the integral on the on the boundary of the two solutions, the non-radial and the radial, equals up to the quotient between the two constants, then you can compare the solution in the Lorentz. You have a Lorentz comparison between the two solutions with the p less or equal than an exponent, which depends on dimension. If you have the normalization which involves the L2 norm of the solution on the boundary, then you gain something. This is the result for general F, sensible to the dimension. What happens if F is constant, is equal to 1? In dimension 2, you have pointwise comparison. In dimension greater or equal than 3, you have Lorentz comparison, which depends if you have normalized in such with the L1 normal solution on the boundary or with the L2 normalization. So once again, you have the dependence of the result on the dimension. What I would like to show you is a sketch of the proof in the case dimension 2 and in the case f equal to 1. The Talenti with the Dirichlet boundary condition and the Neumann and the Robin are not very different, but I will show you the proof with the Neumann boundary condition, but in the simplest case, dimension 2 and f constant equal to 1.
In previous slides, can you explain the very last exponent n divided by 3 and minus 1? I mean, the previous one, this looks like Sobolev.
No. This is not. This happens because you have you can see the proof and you see that you have you use the isoperimetric inequality. And so when you mix the exponent appearing in higher dimension of the isoperimetric inequality with the other exponent, this is the best one that you can.
And the P here could be less than 1, right?
Yeah.
It is not a norm
It is
anymore.
not a norm.
Okay,
It's not.
okay.
Is a comparison, not with something which is not. Okay, let us show the proof in the Talenti case, f equal to 1, and Dirichlet boundary condition, minus Laplacian of u equals 1, u equal to 0. Then integrate formally the equation, the right and the left hand side, on the set omega t, which is the set where u is greater than t. It's measured, I have denoted, it's measured by mu of t, distribution function. Since u is 0 on the boundary, omega t is completely inside. And so if you integrate the equation, you have that mu of t equals the integral formally on the boundary of this set, which is, let me write u equal t, of the gradient of u. Then if you observe that the perimeter of omega t, which is the measure of this red part, is the integral of 1 on the set u equal t, and you use Cauchy-Schwarz inequality, this is the mu of t, because it's the integral of the gradient on the line u. And 1 over is the derivative of the distribution function by Goria formula. The distribution function is the measure of 1 over u greater than on the set u greater than t. And so you have you discover that mu times minus mu prime is greater or equal than the perimeter of this set. And now you use the isoperimetric inequality. And when you use the isoperimetric inequality in dimension 2, you have that p squared is greater or equal than 4 pi times mu. Joining the two inequality, and you have that 4 pi mu is less or equal than minus mu prime times mu. You cancel out mu, and you discover that minus mu prime is greater or equal than 4 pi. But 4 pi is exactly the derivative of the distribution function of the solution in the radial case. And so you have compared pointwise the two distribution functions and then the rearrangement. Why this is exactly equals? Because you can write the solution. Not only the numerical reason, because also if you do the very same computation in the radial case, all the inequality are equality because the set are ball, and so the isoperimetric inequality also like inequality, and also the gradient of the solution is constant on the level set, and so the Schwarz inequality. So you gain that minus mu prime is greater or equal than mu prime, and then you have fixed. Because mu is less or equal than me, and then you have going twice compared the two solutions. What happens in the case of Neumann boundary condition? In case of Neumann boundary condition, and essentially also in the case of Robin boundary condition, you have this fact that the super level set is no more completely inside. Boundary. So you have a piece of the boundary which is inside, and a piece of the boundary of the super level set which is on the boundary of omega. Okay. While in the radial case, the solution is always the same, but it is not zero on the boundary, and so it's constant on the boundary with a positive value on the boundary. And so what happens for the solution in the radial case? When you consider the super level set between 0 and its minimum, it is the whole ball, and then it goes inside. There, and then the super level set are both completely contained. So this is the situation in the radial case. When T is greater than the minimum of the solution, you have ball completely contained, while until the minimum is the whole ball. And in the case of the non-radial, you do not know because it can intersect. So what happens here? Integrate once again the equation on the boundary. The equation, sorry, the right and the left hand side on the set omega t u greater than t. And you obtain that the distribution function equals the integral on the boundary, no more of the modulus of the gradient, but by divergence theorem of the normal derivative, the modulus of the normal derivative, which is the gradient inside, but is the constant outside. No? And so you have you do the very same computation in the sense that you consider once again the perimeter squared of the super level set, which is greater or equal than 4 pi times mu. But here, when you do the Schwarz, the Cauchy-Schwarz inequality, one of the two pieces is mu of t. The other, which is 1 over the gradient, you have to divide in two pieces. One is the gradient, one is the integral of 1 over the gradient inside. Because the boundary of the super level set has a red part which is inside and a blue part which is on the boundary of the set omega. So here, this is mu. This is mu prime, but you have an extra term, which is the integral of 1 over the normal on the part of the boundary which is on the part of omega. In the Talenti proof, you do not have this one. Okay? Because in the Talenti proof, all the super level set is inside. And so the integral on the boundary of the super level set of 1 of the gradient is mu prime, because everything is inside. Now it is not the case because the co-area formula was on this piece. Okay? And so you have an extra term that you have to control somehow in order to compare. So if you cancel mu, in higher dimension here, you have a power of the Lorentz comparison. Okay? Here you have mu, and so you cancel mu, and you discover that 4 pi is less or equal than minus mu primes plus the extra term, 1 over c minus 1 over c is the value of 1 over on the normal, on the blue part, because of the Neumann boundary condition. What happens for the radial case? For the radial case, once again, you have all equalities. You have all equalities because in these inequalities, you have used only the isoperimetric inequalities and the quotient parts. But in the radial case, the isoperimetric inequality holds true like an inequality, and the radial and the quotient parts is in, because everything is in. And so if we are able to compare the extra term with the extra term, we have done. We have finished. We obtain the comparison, the pointwise comparison result. And how we can obtain the comparison of the extra term? Look at this. If you integrate the measure of the super level set intersecting with the boundary between 0 and S, this is obviously less or equal than the integral between 0 and plus infinity of the very same interval. The integral between 0 and S. And I apply Fubini. Once you have applied the Fubini's theorem, on the right-hand side, you have integral of u on the boundary. What happens in the radial case? In the radial case, if you integrate between 0 and S, this is equal to the integral between 0 and plus infinity. Because if S is greater or equal than the minimum, because this is empty. Because in the radial case, when the level set is greater than the minimum, you are completely inside, and so this is empty. So this is, you have equality here. So what happens if you integrate between 0 and S, all this differential inequality and this differential equality, you integrate between 0 and S, and you have 4 pi S times mu minus the measure, because you are integrated in prime, less or equal than this. But this is less or equal than the integral of u in the boundary. In the radial case, you have all equalities. Remember that you have normalized the solution in such a way that the full integral on the boundary equals up to the quotient difference. And then you have that the black part is less or equal than the violet part. And then you gain the pointwise comparison. So essentially, you have proved the comparison result by using the results holds true because you use the Fubini. The idea is Fubini's theorem in order to treat this extra term which appeared because the super level set did not move completely inside by the boundary. And I could also introduce you some other type of symmetrization, but I do not have that. And I stop here. Thank you very much.